the same way with earthquakes. You know, there's nothing that you can do about stopping tectonic earthquakes taking place. So what you try to do, of course, is to build your buildings to be resistant to the shaking of earthquakes. You want to make an earthquake-resistant building. You want to reduce your exposure of people and also the vulnerability of your structures. So it's exactly the same when you're dealing with mine seismology. Over here we can do something about the driving forces, and we'll talk about that later, because you are driving it yourself. You're choosing how big to make your excavation, and then what sequence to make it, and how to support it. But a lot of what we do as in working with our rock engineers and mining engineering colleagues is working together and advising how to make your excavation safer. But one of the fundamental things that we need to do is know the properties of the materials with which we are working. So what we do, and you have you take specimens of the rock in which you are mining. You have various testing machines like this, and this is at our university, but these are pretty standard testing machines that you can use to squeeze the rock and pull the rock apart, see what its compressive strength is and its tensile strength. So over here, these would be typical examples of rock from our deep South African gold mine. So you can see your quartz pebble conglomerate, and in between there you find grains of gold. And we first take our specimens, we make sure that the edges are perfectly flat, because if you squeeze them and they're not parallel and flat, it will give stress concentrations and your specimen will break at a lower strength. And then we stick also little strain gauges on here to see how it responds to the deformation of the rock, because we want to see how elastic that rock is. We want to determine its Young's modulus is what we call it, is its elasticity. So, and then we load it in a machine like this over here. It can put in very, very powerful forces here. Okay, so we want to see what the strength of our rock is, and we squeeze it over here, and afterwards it will fail in some way. Okay, so we can see the whole stress strain curve, how the rock responds to loading. One thing that we also discover is that your rock becomes a lot stronger if it is what we call confined. Okay, if it's just a specimen on its own and it's not confined, it will just crack down the middle at quite a low load. But inside the earth, your rock is embedded in a rock mass, and so it's confined, and that makes it a whole lot stronger. And so we also have what we call these pressure cells over here, where we keep fluids under high pressure so we can simulate better the underground situations and find out how strong it is when it's under confinement. So we do this to do specialized testing. Now this is some work that I did in Canada a few years ago, where there's a very particularly powerful press over here. And what is good about this is often if you've just got a small specimen, smaller than a coffee cup, it's not such a good representative of your rock mass. You've got problems of scaling the properties. You need to look at rocks with some more imperfections in it. So this would allow us to put in a bigger specimen inside here. And what we did over here was not just look at a cylinder of rock that was intact, but we started to make interesting structures like this. So this is a 10-inch cube of sandstone over here, and what we've done is we've cut it, we've carved it in such a way to simulate two pillars over here. And the whole idea was, now as you load it, if you assume that your material is completely homogeneous, got the same properties, you wouldn't know which pillar would break first. It would be just the same properties. But we know in nature, of course, nothing's perfect. One of those pillars will be, for some reason or the other, be a little bit weaker. And then once cracks start to form, it starts to deteriorate, it will start to fail more and more. So this was all part of a project where we're trying to look at how we can do what we call data adaptive modeling of the rock mass response to mining. So the idea was, as we were going to load this, we had various strain gauges and little acoustic emission sensors. You'll see later on we even had a camera inside here. We put all sorts of instruments in here to see how the rock was behaving as it started to fail. And then the idea was that as we started perhaps to see a concentration of acoustic emissions, we'd see that pillars being damaged. That would allow us to recalculate when we would think it would fail. So this was a kind of experiment. We would say, okay, we've built this block over here, we've done tests on core that we got out of here, but at what load will this whole structure fail? Okay, so you'd make a prediction before you started the experiment, but the idea was that as the experiment proceeded and as you were collecting information, could you make an improved prediction of at what load your system would fail and where would it fail. Okay, so that's kind of simulating in a way what you have in a mine, where you've got a complicated structure and your geology's got various faults and weaknesses and different rock types, and you're monitoring the whole time, and what you want to do is to try to understand when your failure would take place. So this is the kind of work that we have done. So you put it in a box here, and we could then load it on the sides as well, so it was also confined with these hydraulic pistons, and there we set it off in motion. Here, my friend Denis Labrie in Canada, and this is just a movie taken with a camera that we had inside, looking inside that tunnel. So our pillars were on each side here, and I've just taken a few frames from this picture. And so this is at the start of the experiment over here at 00 time, and what I've got is a few arrows over here which are going to show we will see a bit of interesting movement. Now that was 1 hour and 30 minutes later, so you can see it's been very loaded very slowly, but you can see there's been a little bit of confinement taking place, and a little bit later you suddenly see a crack starting to appear here in the corner, starting to unzip over here, and you see little bits of rock flour, the rock being spat out from those cracks as the rock starts to fail. And as you go along, a few minutes later, you see the crack is unzipped on the top right over here, and you can see on the floor of this tunnel, this excavation, lots of little fragments of rock that have been spat out. And so we go along, and you can see little rocks being spat out, and now it's starting to get towards failure. And what we did is, as we were watching this, as it started to fail, we slowed down the loading. Okay, and then you even get to a point where you stop the loading, but it just then starts with the weight on it. It starts to run away. It becomes a runaway process to failure. And in the end, you see a lot of debris. You can see the crack disappearing over here. You can see a crack starting to develop in the bottom left-hand corner, a fresh rupture running along the side here. And now you can start to see the whole thing starting to sort of close together. You see that right-hand wall coming in like this, like that, as you go along there. That's after a few seconds. And the crack on the bottom left is starting to develop, and bang, it goes on there and starts to fail more and more. You can see the floor heaving up on the left, and eventually somewhere at this point you can see the left-hand wall cracking up here. We stopped the experiment. We didn't want to destroy all our equipment, we wanted to use it again. So we then stopped the experiment. We took the block out. You can see all the cracks and the damage, so you can inspect it. We also then put it in resin, to stabilize it. We cut it like a loaf of bread, so you could see all the different slices through here and see how the cracks develop through the rock mass. Okay, so you can see on the roof there was a bit of a thrust fault appearing over here in the roof, and the whole idea after that, and I won't go into the details, was then to correlate that information, those observations, with what we observed. So here's some of the acoustic emissions that we were recording. So you could see as our time went by, over 8,000 seconds over here, we could see the initial ramp over here, then a more stable ramp when we slowed the loading, and at the end, the acceleration as we headed towards failure. And so this is, I won't go into all the detail here, but the whole point was, as engineers, and as, I suppose working in rock engineering, we use numerical modeling tools over here which model the stress condition inside the earth, and we use that to kind of choose between different mine designs. So for example, you have to see how big should your pillars be, how big would the gaps in between there, the stopes, the areas that you mine out. And we use numerical modeling tools to make decisions around this, but we need to have good input data, rock strengths, rock properties, rock behavior. And the thing over here, when you're working in mine seismology here and in rock engineering, you're not just working with a rock in one state. Okay, it's not just always elastic. What you find is as you excavate, it changes, the properties change as it starts crushing and losing its strength. And you can find in different parts of your model, different things are happening over here. It's like the rock is undergoing a change of state. It's like working with water, where sometimes it's a liquid and sometimes it's a gas and sometimes it's a solid. And so you have to have your numerical models that can cope with these changes in your, what we call our constitutive equations. So this is the kind of work we were doing over here, and I won't go into the detail over here, but trying to use our, I suppose, our observations. And here you'll see we're not just making, I suppose you could say, seismic observations are a very important part, your energy that's been radiated, but of course you try to make as many observations as you can of the elastic deformation and things like that as well to build into your picture. And in the end, the whole goal over here was to improve our numerical modeling tools so they could take in a rich data set over here and help make predictions as to how your whole system would evolve as mining proceeded. Okay, so that I won't go. That's just a little bit of an idea of some of the ways that the stuff that we do here in mine seismology. Okay, but let's get back to this picture over here. Okay, so what causes mining-induced seismicity? Well, it's because you're making an excavation over here, so your stress is being concentrated on the outside over here, and so sometimes that stress will exceed the strength of your rock. If you make a circular excavation, a circular tunnel, this is something you can solve analytically. It's very simple. You can work out the equations are known as the Kirsch equations, which predict the stress distribution from a circular tunnel, and what they predict is that your stress will be amplified on the edge of the tunnel by a factor of 3 compared to the normal, what we call the virgin stress, without the excavation. So let's say you at a depth of, let's make it easy, 1 kilometer. Normally you try to have one vertical and one north-south and one east-west, but often your bore, your sensors will be orientated. You've got them in that cylinder that you put into the borehole, and so often one will be parallel to the axis of the cylinder and one perpendicular to the axis. And so sometimes, if you can, you make the north, south, east, west. Other times they'll be relative to the axis of your borehole. But as long as you know what your orientation of your borehole is, you should be able to work out, make the corrections, and work out what they are. This is sometimes people make mistakes. And so it's always very important that when you're running a network to check that your orientations are correctly entered. And what you do often is you'll use a remote earthquake, a distant earthquake that comes through, and then they should all be seeing the same sort of sense of vibration. You can check and see if you've got any anomalies there. But in fact, it doesn't matter as long as you know what it is, because then you can work out the frequency of vibration. Some geophones, the lower frequency geophones, it's very important that they're either vertical or horizontal. But if you use the higher frequency geophones, more than 14 hertz, they're not so sensitive, they can be tilted at an angle and they will still work. So it depends on your sense. If you use the accelerometers, they're not, it doesn't matter if they're at a funny angle, as long as you know what the angle is, they will still give you a Right, what I was saying over here is, as seismologists, you normally, I'm sure you would know what P velocities and S velocities are, but you can see your P velocity is dependent on elastic properties, and your bulk modulus, and your shear modulus, and of course your density. And the same with your shear wave velocity. Now, as an engineer, when you're looking at your deformation of your rock mass and how it's going to respond to the excavation, it's important that you know those parameters, those elastic moduli as well, and because you use them in your mine design. Okay, right, here's now, we're looking at detail at a seismogram over here, and what you'll see also I suppose in earthquake seismology, you tend to just work with, perhaps, of course, your location is very important, and then you want both your depth and your epicenter, and then you want to know something about its, perhaps, a magnitude. Okay, and we know we might use the local magnitude or the Richter magnitude, but we know that's just an empirical method. If we want to know something more scientific, we get the moment, okay, the seismic moment, and you can also from any seismogram get the energy that's been radiated from the source. And now in mine seismology, we'll talk about that a little bit later, but from that we can derive a whole lot of other information about your seismic source. Okay, and something that's very fundamental over here is looking at what you call your corner frequency, your dominant frequency. So over here you can see a seismogram over here. The whole window length from left to right is about 390 milliseconds here, so this is about 400 milliseconds. And here you can see a wave over here, and you can see that it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe 10 times in 400 milliseconds, so you know that's about 40 milliseconds length. So you can work out what its frequency period of perhaps 40 milliseconds. Okay, 1000 divided by 40 is 25 hertz. So that would be a dominant frequency of about 25 hertz. Now that frequency is very important about telling you about the source. It's
corner frequency, what the dimensions of the source are. And from that you can start working out other things when you use your energy and your moment and combining them and get an idea of what your stress drop is. What is the change in stress with that seismic event? And so we use these parameters over here later on to derive a whole lot of other parameters that we use to try to characterize our rock mass. Right, so other important parameters that we have to deal with over here is the change in amplitude. Okay, what we want to do over here, and that equation here just tells you how your amplitude varies with distance as a function of your geometric spreading, but as a function of your attenuation of the Earth, or Q over here. Now this is something also that when you're working in the mine, in particular when you've got excavations around here, your rock mass can be fractured and damaged. You can get big variations in that Q value. And so when you're trying to I suppose determine the size of your source, the amount of energy or moment released, you have to take that into account as well. Of course, you also have to look at what is the location of your sensor to the source. And if you've got a ray path that would go through an excavation, your energy will still leak around it, and you'll still get an arrival there, but it will be very much delayed, and it will be distorted. So again, this is something as you analyze, is you have to, you'll get a quick and dirty location, a fast location, but when you want your accurate location, you have to consider all your arrivals, and you'll discard a whole lot of them because they would have been in the shadow of an excavation, or the ray paths would have gone through a fractured zone, for example. And that would distort the energy and give you a bad image of the source. So that's again another difference, I guess, from earthquake seismology. We can pretty much use all your sensors that have got decent recordings. Here we have to take into account the effect of our excavation on our ray paths. Okay, another thing that we find very useful is, and depends on when you're doing more kind of analysis, is what we call our coda wave. Okay, if you just have a single sharp arrival, seismic event, you'll get a nice P wave and a nice S wave. But what we often get over here are a lot of reverberations that come after it. Okay, and these, on the one hand, this is just your energy that's been bounced around from excavations, from other kinds of reflectors. And what we can do, and this is when we are trying to characterize our rock mass. I mean, what we're trying to do in mine seismology is to see how your rock mass is changing with as mining proceeds, and if there are some signals that can indicate that it's starting to get damaged and a big seismic event could occur. And one of the more, I suppose, advanced analyses, this is not done routinely, but is to do analysis of this whole coda over here and seeing how your coda, how your reverberations afterwards change with time as your mining proceeds. And particularly then you'll be choosing ray paths that go from a seismic event near the excavation and to another sensor, because this is giving you not real time but near real time information about changes in your rock mass property, which could be related to the preparation for a seismic event. So we both will look at how the energy tails off over here and how the frequency changes over here to see whether it's due to scattering or absorption. So this is another kind of analysis that we will attempt. Okay. Now let me just, what you see over here, when Ranta asked earlier, how do we know whether it's a mining related event? Generally this is just showing our excavations here, where we're working out here. You'll find most of your energy taking place close to your excavation, your seismic events close to your excavation, so it's quite clear it's related to mining. So where they happen, they usually happen close to mining. Sometimes you find very interesting properties over here. This is a section through the earth over here, and this is where it's been mined out over here. This is a tunnel, a horizontal tunnel, and here a pillar was left behind. Okay, so it wasn't mined out here, this was part of your rock support. And what it was found over here is that your pillar was stronger, the rock making up your pillar was stronger than the rock in the footwall. This was a quartzite, and this was like an argillaceous quartzite with shale in it. And so what happened as the load came down, your pillar punched into the footwall. It's a pillar punching event, and that's where your main event was. and that's where you've got a whole lot of aftershocks over here. You can see your pillar was actually sort of intact and pushed into your footwall. So we've got what we call pillar foundation failing. Okay, so this is the kind of situation that you are in, is using your seismicity to understand how your whole rock system behaves. When do they happen? Okay, as I said earlier, that you can see this is the time of day and the number of events here. You'll see in this particular mine a very strong peak in your number of events between 5 and 6 in the afternoon. And that's because your blasting time would normally be between 5 and 6. So that's the time when you trigger off most of your seismic activity. And then you evacuate your mine, typically for a few hours, for 6 hours, because you need the dust to be cleared, you need the poisonous fumes from the explosives to be cleared, and you also want your seismicity to die off. So and then your night shift will go in and they'll move the broken rock out, and then your day shift will come in to blast, to prepare the holes for your next blasting round. But the thing is that still you'll get seismicity happening all through the day, and you find that your bigger events are not so much controlled by blasting time. They tend to happen randomly through the day. And so I suppose one of the big issues is could we move from using blasting to using other kinds of mining where you could mine around the clock, 24 hours around the clock? And you certainly can. The question would it change your seismicity? And the research that we've done has said, no, your amount of seismic energy that gets released is proportional to the amount of mining you do. Okay, it's to the volume of rock you extract, to the change in energy balance that you do. And so whether you mine by blasting or whether you mine by cutting the rock or doing it non-explosively, you're likely to get very much the same amount of seismic energy. Currently, when you are blasting, you still release quite a lot of the energy at what we call blasting time and when your mine is evacuated. But if you were mining around the clock, you'd have, your risk would be distributed all the time. Of course, the thing is with mechanical mining, the hope is to take people out of the mine. So you mine safely, you remove people from being exposed to that, or you have them working and remotely controlling the equipment so they're in a safe place. So there are different ways in which you can handle this. But certainly events tend to happen very much closer to your at your blasting time. And then even if you look at during the day of the week, okay, in South Africa we don't blast on Saturdays and Sundays. We will do some maintenance here, but you'll find out that as you start blasting Monday, Tuesday, Wednesday, you're really perturbing the rock mass, and it's get most activity, perhaps normally on a Friday. It's the kind of accumulation of the week. You don't blast on Saturday, you've still got that perturbation, drops off on the Sunday, and then builds up again. And again, this is due to your whole mining cycle, your mining activity. So this is why we want to try to almost predict your, if you do working with earthquake seismology, you kind of assume your plate tectonic forces are more or less constant the whole time, and you're looking for seismic activity changes. But here where you're mining, you drive in it the whole time by putting in other perturbations of your system. And that makes it quite difficult to separate the signal coming out that's saying, hey, here's a fault that's preparing to slip, it's about to fail, from the effects that are being produced by your daily blast. Okay, I won't go into all the location stuff over here. The location stuff is pretty straightforward. But one thing that I haven't really heard spoken so much about yet is the Wadati diagram. Any of you know what who does know what a Wadati diagram is? Okay, you know what a Wadati diagram. This is a very useful plot over here, because as I said, often with you have a seismic event and you want to locate it accurately. But we have so many events happening on a mine. Often you might find two unrelated events, different parts of the mine, happening at more or less the same time. And so on your seismograms, you've got a problem of associating a seismogram with a particular event. Okay, and some of them might get confused. Also, you all have ray paths that have been delayed because there's been an excavation in between, and so your ray path hasn't been able to take the shortest point, it's taken a longer point, so it's got there a little bit later. And if you use that in your location, your straight ray path assumption is completely invalid, and it will give you a bad location, or make your location worse. So you want to get rid of those. You've got you just use your good events, you rather discard a few bad events. So what we plot quite routinely is just on the one axis, you've got your P arrival time for an event. You've got, in this case, 2, 4, 6 events over here. So it's your P arrival time, and over here, your difference between your S time and your P time. Okay? And if those events are all from the same source, and they've followed more or less a straight path, if you plot your P arrival time here and your S minus P time here, they should plot along a straight line like this. Of course, there will be a little bit of scatter because there are variations in seismic velocity, but it will enable you, if you find a point or two that plots off here, then you know they don't belong to that system. It's either been a misidentification of a signal from another event that just happened to occur near a seismometer at that time, and you've made a false pick, or else it would be a ray path that has, been taken a longer distance. So this is something that we will often do. You'll do your first quick location using all your data. By least squares, you get a reasonably good fit. But afterwards, you do a more detailed analysis and discarding the bad data. Okay? And so this is a very useful tool that we use to improve our locations. Okay, I won't. Okay, what do we determine from our seismograms? Okay, there are 4 independent parameters you can get from of a seismic event. You can get the time it occurred, okay, T0. You can get the location, X, Y, and Z, okay, and then you can get the energy and the moment, okay. And generally, you could say the bigger the moment, the bigger the energy. But still, those are independent parameters. If you get a event occurring on an old fault, a mature fault that's got weak gouge, you can get a very big moment, a very big co-seismic displacement, but the energy will be relatively low, okay, because but as compared to, say, a fresh fracture in intact rock, where perhaps you'll only get a few centimeters of movement, but you break in fresh rock, and so you'll could get high energy and low moment. So energy and moment are different parameters, and they tell you different things about the source. So we always, from a seismograph, just by looking at the energy and the vibration, you can estimate the energy of the source, and that is expressed in joules over here. And seismic moment you get from analyzing the frequency spectrum. So now this is a very important, I suppose, topic in seismology. Over here is spectral analysis. Now this ties in very closely with what Fabio did yesterday when he was talking about your response spectrum for buildings. It's a similar idea. But what you do over here is you take your seismogram and you do a Fourier transform. So you decompose it into the amplitudes of all the frequency components, and you plot it here on a graph. Okay, now traditionally what we do is we plot the displacement spectrum. Of course, you can plot the amplitude spectrum, or you could cross the displacement spectrum, you could plot a velocity spectrum or an acceleration spectrum. But normally we take our geophone recording, we integrate it to displacement, so we get our velocity, displacement trace, and then we do our Fourier analysis. And theoretically, what you should get, your model over here, should have a low frequency plateau. So you can go from 1 to maybe in this case 10, 20, 30, 40 hertz over here, and then you get a fall off over here. And this, we call this the corner frequency over here. You fit a line to the low frequency plateau and the high frequency fall off. This would be your dominant frequency. If you had taken your velocity trace and you'd done the Fourier spectrum, then this would have had a shape something like that. Okay? And this corner frequency is a very important measurement that we use to determine other derived properties. So this, every record, every seismic event that's recorded, all the traces, will be windowed, will be Fourier transformed, and we will fit a model to it in order to get your source parameters. So that is routinely done. Okay, and so this is the formula over here. We won't go into the detail, but tells you that your moment over here, m0 over here, okay, is related to the sigma 0, which is your low frequency spectral plateau. So that from that you can derive your moment of your event, and once you've got your moment, you can start doing all sorts of other calculations. So in seismology, and also in earthquake seismology, one of the famous models that we use is the Bruin model. And this tries to describe your source as what he called over here a penny-shaped crack, a circular fault along which you would have had a constant amount of slip. Okay? And if you've got your corner frequency over here, and you know what your shear wave velocity is, you can work out what you call your Bruin source radius. Okay? And you can also work out what we call the static stress drop. And so this is your static stress drop. So you can work out how big your stress drop was. What you'll see over here from this equation, see on this equation here, let me just go down slightly. Okay, you'll see that over here there's a R naught, that's your source radius cubed. Okay, and now that could be a problem because you can see the amount of your stress drop will be very critically dependent on your source radius, and if there's a bit of an error there, it will make a big error over here. And so you have to be very careful when you compute your source radius over here, make sure it's reliable and that it's sensible, or else you'll get a crazy stress drop here. So that is the kind of parameters that we derive in mine seismology that we routinely use. Is not just magnitude and location, but we derive moment, we derive energy, and from that we start to work out a whole lot of other derived parameters as well. Okay. Right, now what I want to move on to over here are some of the effects of an excavation. One of the things that we've specialized on is making these measurements on the wall of our excavation here. Now when a seismic wave travels towards the surface of the earth, okay, and gets to a free surface, what you'll find is that you get a doubling of your amplitude on the surface of your excavation. That's because when it's traveling through the solid rock, it's pushing against something the whole time. But when it gets to a free surface, there's nothing to stop it there, and so you'll in fact get a doubling of your amplification, your amplitude. And so at the very least, when a seismic wave comes in here on the solid rock and comes to the wall of your mining excavation, you get a doubling of that amplitude. So often this is something that you have to bear in mind. Seismologists sometimes have their measurements of amplitude in solid rock over here, and they assume that's the amplitude that you'll get on the skin of your excavation. What you also find, as I showed you before, around a deep excavation, you get a whole envelope of fractured rock over here. Now, that fractured rock has got very different properties to your solid rock, and it acts and it kind of traps the energy in there around your excavation. So what you find, in fact, is that your amplitude around an excavation is usually your amplitude of motion over here is usually, and this are just measurements where we've had sensors on the wall of the excavation, on the roof, and 10 or 20 meters in the rock, and you find that this is the peak particle velocity that we would have recorded on a sensor in the rock, and these would be our particle velocities on the skin of the excavation. And we get an amplitude of anywhere between 4 times, between here and here, between 4 and 10 times greater amplitude. So in earthquake seismology, you talk about site effects, site amplification effects, and here this is the underground equivalent of this. So exactly in the same way.
Okay, I guess we're ready, aren't we? Okay. Safa.
Yes.
Are you ready?
Yes.
Okay. Just a few minutes, please. Okay, the program today will be the talk. It starts from 9:30 to 11. And after that, we have our colleague from the main center here, Aswan, who will talk about the induced seismicity, Professor Haggag, who will start from 11 to 12. And the coffee break will start from 12 to 1. and we'll make this chance just to do our break because today is a Friday. Okay, so 12. 1 is a coffee break and also a break time for us. And after that, Mustafa will start from 1 to 2:30 lecture. Is that okay, Mustafa? From 1 to 2:30. And after that, so Rana first? Okay, so Rana before you. Okay, so Rana, you just told me that you just need 30 minutes.
Yeah.
Okay, 30 minutes is enough. Is it enough for you?
Yeah, that's enough.
Okay, so Rana will start from 1 to 1:30, and after that Mustafa from 1:30 to 3. No, sorry. We need to also, our lunch will be from 2 to 3. The lunch. We start from 2 to 3. And after that, so you can take just 30 minutes, Mustafa, or just 1 hour, and we can complete after lunch. Is that okay for you?
Yes.
Okay. And after that, we have a visit here in the main center to see all how the system is working here, our network, okay, the center, and something like that. But this is all after our sessions. Okay. Please register.
Okay. Thank you, Ahmed. One of the things that has always interested me is our stories about the origins of earthquakes, what causes earthquakes. And so I found this here on the internet, and being in Egypt, I thought, well, let's see what in Egyptian mythology is seen as the cause of earthquakes over here. And so this is what I found. It says that Apep, or Apophis, was an evil god in Egyptian mythology, the deification of darkness and chaos, and thus the opponent of light and order and truth. And then in order to explain certain natural phenomena, it was said that sometimes there was this battle between good and evil, and sometimes this resulted in thunderstorms and earthquakes. And so I think this is, I forget where this came from, this is a drawing showing this evil god that in mythology here was blamed for the causing of earthquakes. So I don't know if there are any Egyptian people here. Is this, have you ever heard of this before? Is there any? No? Yes? No? First time for you. Okay, I'd be interested. But we can move, of course, here we in Aswan, and we're on the right next to Lake Nasser and the high dam, and where it causes, one of the big issues, of course, is the seismicity that's induced by the water. And so we'll move down to the another big dam in Africa over here, and that is the Kariba Dam. So Brass Navy and Ezekiel would be familiar with this. And there at Kariba Dam, you see a carving, a soapstone carving over there. Brass Navy, do you know who that is? Nyami Nyami, okay, and there's a story, the belief of the people who live in the Zambezi Valley is also in many African mythologies. There's the legend of the river snake, you know, to say to children, don't go to the river, it's dangerous, there's a snake will catch you. And so, but of course, after Kariba was built over here, there was a whole lot of reservoir-induced seismicity. And the story that developed around here was what happened is that Nyami Nyami had gone down the river to visit his friends, and when he came up again, he found the dam blocking his way, and he couldn't get back to his wife. So he was angry from time to time, and when he gets angry, he shakes around, and that causes earthquakes. So it was just interesting to me that, and I've got a statue like this. You can buy the carving here in my office in Johannesburg of Nyami Nyami, the earthquake causer of Southern Africa. Yeah, so just something interesting, and another case of induced seismicity here. Right, what I'm going to be doing here is, and passing around, there should be some a flash drive with some documents over here. Now, one of the documents, there's a chapter for a book on rock mechanics and rock engineering, which is in press right now, and published by Taylor and Francis. And I was asked to write the chapter on microseismic monitoring. So that you will get, and it goes into a fair amount of detail. And I'll be using that as partly to cover it. And then the other document you'll find over here is some course notes over here by which we use to teach our mine seismology course. But I'd just be interested to know who here has actually been in an underground mine. Which mine was it? What do they mine? And what did you do there? Is there who here has been down a mine? Which mine have you been down?
Underground mine
for gold. And how deep was it?
I didn't go so deep, but I
yeah, but as far as you know, so far about 300-400
meters. Yeah. Who else has been down underground in a mine? Gladys, which mine have you been down?
Which mine? Tautona, South Africa. What did you do there?
Well, just to see.
Just to see. Do you know how deep it was? Yeah, Tautona is one of the world's, it is the world's deepest mine. It goes down to about 3.9 kilometers below the surface. Okay, anybody else here been to a mine? Mustafa, you've been down a mine?
Yeah, mine, an incredible accident in Northern Africa where water exploded mine and went down the mountain.
Okay, and were the miners, were they successful in the rescue?
Well, some of them, they passed away.
Yeah. Ronan? What
Yeah, a long time ago I went down a mine in northern France. At the time they were mining seeds about this big.
Yes.
So it was the end of the industrial period.
That was a coal mine, wasn't it?
Coal mine.
Yes. Yeah. Okay, so anybody else who's been down a mine? Yes, Tiff?
Yes, yes, from Kola Copper Mine.
Yeah. In Zambia?
Yes, yes.
Yeah.
It's quite very big and scary.
Yes. Yeah. Great. Anybody else? Ross, have you been down? Where have you been down? Outputsong. So that's a South African, another one of our deep mines, our project mines. Sorry? Wanky coal mines. Yes. And there, I mean, a few years ago, many years ago, there was a big disaster at Wanky coal mines, wasn't there? Anybody else been down the mine? Yes, Hazem? Okay, and where was that? Aswan. Okay. And about how deep was that? Quite shallow. Okay. So, yeah, so I can see there, some of you, of course, others have been down caves, but to see that people have been underground, okay, but many of you I see haven't been underground, and so this is quite a different environment in which we go into. But one thing that's for sure, I mean, on our planet, we either grow stuff like to eat or to build with, like wood, or also mine it. And so, you know, mining is our civilization is dependent on mining, and as our shallow resources are exhausted, the mines are going to get deeper. And of course, you have many open pit mines, open cast mines, but you get to a point where it's no longer economical to just make a bigger and bigger pit. You get a little bit of ore down, and then you go into a transition phase where you sink shaft, and you find that the ore body continues to grow to depth. We go from an open cast phase to an underground phase. And so as long as we need iron and steel and all sorts of metals and minerals, we will continue to mine, and our mines will get deeper. And as you'll see, one of the inevitable results of deep mining is that you start to make earthquakes. Okay, now how do you know about that happening? Well, in your country, as the mines get deeper, well, generally your national network is quite sparse, and so perhaps you'll only be picking up events that are bigger than magnitude 2 or magnitude 3, but often the events that happen in a mine will start off quite small, magnitudes of 1 or 0 or 2 and a lot smaller, and so those won't be picked up in your national network, but the people in the mines will feel the shock, and they will cause falls of ground, rocks to be ejected or shaken loose, and that could lead to losses of production, damage to equipment, and of course loss of life. And so that's what we will be talking about now. But all I want to do is, I've got 90 minutes, so I'll be giving you a few ideas about mining and mine seismology, and how it's very similar to earthquake seismology, but also in some important ways quite different. Okay. Now, with tectonic seismology, we understand with plate tectonics and things like that, what drives the energy. Where does that energy come from? It's from plate motions, and it's know that Africa's crashing into Eurasia, and so you get fold mountains and you get tectonic energy being released. But in mining, where does the energy come from? Well, it's quite straightforward. If you've got a solid earth over here, the rock has got weight, so it has a load down below, and the moment you start making a cavity over here, you're making an excavation, the force that would have been transmitted through that cavity, has to go somewhere. Okay? And what happens is that it gets diverted around your opening, and you get your stress being concentrated around the outside here, and so you get big increases in your stress around your excavation. Okay? And you get to the point where that the increase in stress becomes greater than the strength of your rock.
Okay, now, people with, when you start working in mining seismology, you start to use a lot of, I suppose you could say, engineering properties. And one thing you need to know is what is the strength of your rock. That becomes a very important parameter, because that's what provides the support. So, what we do quite a lot of now, how many of you have worked in a rock mechanics laboratory where you've done tests of rock strength? Have anybody here worked in a rock mechanics laboratory? You've had a visit. Okay. So when you get into, say, mine seismology, quite a lot of what we do is we spend time in, and I do, is in rock mechanics laboratories. Let's find my picture here.